Okay, so here's the Unit 6 practice test. Starting out, we got our equations up at the top. The wave speed equation, frequency times wavelength, that weird upside down y is lambda, that's for wavelength. Periods time over cycles, frequency cycles over time. These two are reciprocal to each other. So for the first one, we're supposed to draw a wave with a wavelength of 3 meters and an amplitude of 1.5. I'm going to choose to do every 2 boxes is 1 meter. You get to make that decision on your own. I just feel that doing every box being half a meter is going to make it easiest on me. And that's the way we want to do it. Okay, now I know it has a wavelength of 3 meters. So if I'm drawing it crest to crest, if I start 0 at a crest, that means at 3 meters I'd have a crest, and at 6 meters I'd have a crest. Now, if my crests are at 3, or every 3 meters, that would mean 1.5, 4.5, and then 7.5. Boop. I would have a trough. So then halfway in between here, so right about there is where I'm going to pass through. And there we go. Oh. Okay. So that's what I'm expecting you to be able to do. Oh man, crest at the crest. Okay, for the next one, find the frequency of a wave that has 40 crests that pass a point in 2 seconds. So we've got to find frequency. So that's the frequency formula. So I go frequency is the cycles divided by the time. So there's 1 crest per cycle. So 40 crests. We got 2 seconds for the time. So we can just plug this in simply as 40 over 2 is going to be 20. And then it's hertz. What is the period of the wave in question 2? Period and wave are very closely related. Period is the time for 1 cycle to pass. So period, we can actually solve this one 2 ways. We've got time over cycles, which would be 2 divided by 40, which is going to get me 0.5 seconds. So it would take 0.05 seconds for 1 wave to pass. The other way to do it is to do the reciprocal of the frequency, so 1 over the frequency, so 1 over 20 is 0.05 seconds. If the wavelength of this wave is 0.5, what is the speed of the wave? So wave speed, v, is equal to frequency times lambda. We know what lambda is because it says if the wavelength of the wave is 0.5 meters. So wavelength is a length. It should be given in meters. We want to know wave speed, that's v, and we know what the frequency is from number 2, that's 20 hertz. So we would do 20 times 0.05. So what's half of 20? It's 10 meters per second. For number 5, if wave interference causes the resultant wave to have a smaller amplitude, is it constructive or destructive? It's going to be destructive. So to explain this, to get an amplitude that's smaller, they're going to have to be on opposite sides of each other, so a positive and a negative. When these two overlap, it's going to make a slightly smaller wave. The amplitude's not going to be as great. you wouldn't get as much energy being carried from a destructive interfering situation. Okay, find the amplitude of the resultant wave for a -3 meter wave and a -5 meter wave. So we've got a -3 meter wave, and a -5 meter wave, and they're coming at each other. Now, since these are both negatives, this is going to be constructive interference. It's going to be constructive because we always add these things up. -3 plus -5 gets me -8. Whoop. So this wave is bigger than either of these two waves. We've got constructive interference going on. A beam of light strikes a piece of glass at a 45-degree angle. So this coming in here is the incident ray. Draw the reflected and refracted rays below. So the reflected ray is going to be bouncing back here at the exact same angle. So one good way to represent that would be to just say, so seriously draw our little angle here and put 45 and put 45 here. The law of reflection says that the angle of incidence has to equal the angle of reflection. Then we're going to get some portion of this ray that is refracted. If the glass has a higher index of refraction than the air, then it's going to bend downward through the glass. So the original line of the line from the angle of incidence would be like that, and this bends downward more perpendicular. Going on to the backside, what happens to the energy the wave carries when the wave is absorbed by its medium? The medium gets hotter. Basically, this is describing radiation, the way that we pass heat in Unit 5. So if an object is receiving energy from radiation, it's going to get hotter. The way to understand this is if you have like a white t-shirt and you got a black t-shirt and that one's not cut well at all. So this black t-shirt is going to absorb more colors of light than the white one. So we've got 3 colors of light, red, green, and blue. The red, the green, and the blue all get reflected off of this shirt and into your eyes. That's why we see white light. Black objects absorb red, green, and blue. They don't get reflected off, so they're going to get a little bit hotter. So this one's going to absorb more. It's going to warm up more. Draw a standing wave with 4 nodes and 3 antinodes. Here's the thing. Whenever we're drawing a standing wave, the nodes are always going to be on this midline. And we want to divide them up as evenly as we can. So that would be 1, 2, 3, 4 nodes. So these nodes are the points that do not move on the standing wave. The antinodes are going to be the points that move the most. We used to call, with traveling waves, we would call them crests and troughs. But since this is a standing wave, this crest is going to, in a couple seconds, become this trough, and vice versa. Crests become troughs, troughs become crests. If this standing wave had a wavelength of 2 meters, so that means one wave is 2 meters long. The wave goes from here to here. That's one wave. How many waves do I have in that standing wave? That's 1.5. So if the wavelength is 2 meters, so if I take the wavelength and I multiply by the number of waves, it should be how long the medium is. Now this only works for standing waves. So wavelength is 2, number of waves is 1.5. I'm going to get a medium that's 3 meters long. That makes sense, because if these are divided up equally, then 1 meter would be here, 2 meters would be here, 3 meters would be there. On a xylophone and on any musical instrument, the lowest notes are going to be from the longest or largest objects. So, once again, violins are small. They have a higher pitch than a viola or cello or a string bass. So, highest natural frequency is going to be here. Lowest natural frequency would be here. So this is like why, larger gentlemen seem to have deeper voices. Well, they actually have deeper voices because they are larger gentlemen. So, well, at least that's a part of it. Okay, how can glass be broken by singing? Well, geez, that sounds familiar. Wonder why I keep asking this. So, if we've got the glass, and we've got somebody singing at it. Still not good at drawing. Oh, yeah. Yeah. This guy looks like he's straight out of The Hills Have Eyes. Anyways. So. This guy is singing with a certain frequency. Actually, I should really draw this as a longitudinal wave, yeah? So, oh, that's no good. Now he just looks like he's puking. Oh well. The waves coming out of his mouth are now green, and they look like this. They're longitudinal waves coming at that glass. Now, the glass itself has a natural frequency, so if we went ding, it'd make a pitch. He has to match the natural frequency of that glass to get it to vibrate. If he can match that natural frequency, it'll vibrate to the point that it shatters. And then the last one, on the decibel scale, every time we go up by 10 decibels, something gets 10 decibels louder. So if we go from 40 to 80, 40 to 80 is, or 40 to 50 would be 10 times louder. 40 to 60 would be 10 times louder than that. Oh, wait. 40 to 50 would be 10 times louder. 50 to 60 would be 10 times louder than that. 60 to 70 would be another 10 times louder. 70 to 80 would be another 10 times louder. So we would get 10 times 10 times 10 times 10. That is 10,000 times louder. So basically, when we're talking about the decibel scale, every increase of 10 decibels is 10 times louder than the last. So if we're talking about, the difference between a whisper that's like 20 decibels and somebody shouting that's somebody shouting that's like 80 decibels, that would be 6 times you're going up by 10. So 10 to the 6th power, you get 1,000,000 times louder. Okay? Okay.